Let's examine some more associative operations. We have seen the definition of associativity, as well as the consequence that for associative operation, two expressions with the same list of operands will evaluate to the same result regardless of the parentheses that we insert. And in terms of reduce and parallel reduce, what this means is that regardless of the shape of the tree, if the list of operands is the same, we get the same result. But to make these observations useful, we need to have examples of relevant associative operations. When we discuss associative operations, it's important to differentiate associativity from commutativity. Commutativity just means that for a binary operation, we can swap the order of the two operands. Now, while there are operations that are both associative and commutative, in general, these two properties are independent. And in fact, there are associative but not commutative operations, as well as operations that are commutative but not associative. And keep in mind that for correctness of reduce, what we need is precisely associativity. Here are some examples of operations that are both associative and commutative. Many of them come from operations on numbers. Addition and multiplication of mathematical integers, which we can faithfully represent as big-ins in Scala, as well as exact rational numbers, which we can represent as, for example, pairs of big integers, are associative and commutative operations. Moreover, if we perform addition and multiplication modulo some positive integer, such as 2 to the 32, and this includes then usual arithmetic operations on int and long data types in Scala, then we also obtain operations that are both associative and commutative. Another important class of operations that are associative and commutative and have many other properties are operations of union and intersection. Symmetric difference of sets is also an example of such operation. When we manipulate collections, often the multiplicity of elements is also important. That is, whether some element appears multiple times. We call such view of collections bags or multisets. When we perform an operation such as union of bags, preserving the multiplicity of elements, that turns out to be also both commutative and associative. In logic, Boolean operations such as conjunction, disjunction, or exclusive OR are also both associative and commutative. Furthermore, operations on structured objects such as polynomials have also commutative and associative addition and multiplication. Addition of vectors is furthermore associative and commutative, and so is addition of matrices of some fixed dimension. As one of our first examples, we have used array norm that computes the set of array elements raised to the power p. Which combination of operations does this expression correspond to, now that we have seen operations such as map and reduce? We can express the value of the above expression as taking the array A, then doing map on this array with the operation that takes absolute value and then raises it to power p. This conceptually gives a new array, and then we sum up the elements of the array. Summing up the elements of the array can be done by doing reduce with the plus operation. This is justified because plus is in fact associative. You may recall from our implementation of array norm that we only had one traversal of the array, and this is because this map can in fact be combined with reduce. Because map simply applies a given function to every array element, we can apply that same function at the point where reduce would retrieve the elements from the array. This avoids the overhead of building intermediate collections. This improves both memory and performance characteristics of our program because we avoid this unnecessary allocation. In addition to examples of operations that are both associative and commutative, there is a number of operations that are associative but not commutative. A prototypical such operation is concatenation or append of lists. The associativity holds for the append operation, but it is not the same if we compute x concatenated with y or y concatenated with x. These are two distinct lists that happen to have the same length, but the order of elements is not the same. Closely related example is concatenation of strings, which can in fact be viewed to some extent as lists of characters. Matrix multiplication is another example of operation that is associative, but it is not commutative, even when we could both compute a times b and b times a. In general, of course, it need not be the case that b times a is even well defined when a times b is well defined. Analogous situation arises with composition of relations and composition of functions. Composition of relations collects all elements that are pairs of A and C, such that there exists element B where AB belongs to the first relation and BC in the second relation. And composition of functions can be viewed as a special case of that, occasionally with different conventions on the ordering of the operands. For all these operations, because they are associative, reduce gives the same result as, for example, reduce left, even though they are not commutative. Now, as a warning, there are operations that are commutative but not associative. Here's one example. Function f of xy defined as x squared plus y squared. It is easy to see that x and y play symmetric role, so f of xy is x squared plus y squared, whereas f of yx is y squared plus x squared. On the other hand, if we compute the two sides of the associativity law, on the left side we get x squared plus y squared squared plus z squared, and on the other side we have x squared plus the square of y squared plus z squared. And these two expressions are easily seen to be distinct for many values of x, y, and z, because, for example, the degree of x on the left hand side is 4, where it is 2 on the right hand side. So because of such examples, it is important to keep in mind that proving commutativity alone will not be sufficient to imply associativity, or that reduce gives the same result regardless of the order of operations. In general, if f is a commutative operation and h1 and h2 are two functions of one argument, then the function g defined by applying h1 to each of the arguments, then applying f, and then applying h2 to the result, remains commutative. Indeed, g of xy is equal to this expression, but if we swap the arguments of f, which is commutative, then we obtain the following expression, and this is in fact g of yx. So g is commutative. As we have seen in the previous example, however, g loses the property of associativity even when f did have it. The previous example was an instance of this phenomenon when h1 was x squared and h2 was identity function. So when combining and optimizing some combinations of reduce and map invocations, it is important to keep in mind that applying such functions to arguments of some associative operations may lose associativity. It is important to keep in mind that some ubiquitous floating point operations corresponding to important real number operations turn out not to be associative. In fact, even addition of floating point numbers is not associative, although it is commutative. Here we have an example where we evaluate an expression in two different orders and we obtain the value that is not equal. Here I define some concrete values as an example for when this can happen. We define e to be a very small positive value. X is a very large positive value, and mx is a very large negative number. Now, x plus mx will be 0, and when we add e, we will get this very small positive number, e. On the other hand, what happens when we compute things in different order with different parentheses? Well, mx plus e, unfortunately, cannot be represented precisely, and because we do approximation, the value of e will essentially be lost. So this expression will evaluate to mx, and when we add x and mx, the result will be 0. And this is why we obtain violation of associativity law. Equally simple examples allow us to illustrate that multiplication is not associative either. Here, in fact, we can use some of the same arguments. So e times x versus e times x squared. For appropriately chosen values of e and x, this evaluates to false. We can again pick e to be a very small positive number and x to be simply a very large positive number. Then e times x is in fact 1, and when we multiply it by x, the result is x, which is a very large number. On the other hand, x times x is not representable at all because it's too large, so the result is infinity. Now, floating points define rules for how to compute with infinities, but certainly the resulting equality does not hold. The previous operations were in fact commutative, so it is interesting to think why it was possible to make such approximate operations commutative, yet the designers did not succeed in making them associative. Well, it turns out to be much easier to make an operation commutative. Suppose that we have some operation g that is not necessarily commutative, but we are happy with answers gyx or gxy. Then all we need to do is pick some total order on the values from our domain, such as x and y, that allows us to compare two values such that always we get the answer that they are equal or one of them is less than the other. We can do that by, for example, comparing raw bit representations of these values, although there are for every domain better ways to do that. We can then define function f such that it computes those among the values g of xy or g of yx for which the first argument is less than the second. It is straightforward to verify then that such slightly modified operation f is in fact commutative even if g was not commutative. Of course, when the two arguments are equal, then it doesn't matter whether we compute g of yx or g of xy. The result is equal to, for example, gxx. And if we have that y is less than x in our ordering, then the left side is g of yx, because we execute the true branch, whereas when we compute f of yx, then we will execute the else branch, which will lead to exactly the same invocation of g. So regardless of what the value of g is, we'll obtain the same value for f of yx and f of xy. So there are some ways of patching functions to make them commutative, but we do not have such trick for associativity of functions.